Are there any theorems in evolutionary biology? You're all probably familiar with Pythagorean's theorem from geometry, or maybe the binomial theorem from algebra, but are there any analogs in the field of evolutionary theory? Welcome back to the channel. If you're new here, I'm Zach Hancock, an evolutionary biologist, and today we're going to take a broad, sweeping journey through an array of important topics in evolution, ranging from the evolution of altruism and spite, to evolutionary game theory, and finally, to the fundamental theorem of evolution. This might seem on the surface like a ton of unconnected topics. Seriously, Zach, just split this into 3 videos. But each of these topics are connected to the life and work of a man named George Robert Price. You've never heard of this man, but he is responsible in no small way for each of these 3 big topics. Hence, this video will be structured around his life, breaking off as appropriate chronologically to evaluate the mathematical and conceptual underpinnings of each of these topics. In this way, this video will be a kind of mix of the formats in my previous ones. The history will guide the discussion of the theory. However, before getting started, I want to insert a trigger warning here. While the contributions of George Price to evolutionary theory are incredible, his life was greatly colored by tragedy, anxiety, and depression. We will be discussing issues related to mental health and suicide. We will not shy away from details, so please be prepared for this as we plunge ahead. I hope you enjoy this fascinating story of evolution's most fundamental theorem and how it relates to game theory, kin selection, and the evolution of altruism, all connected through the curious life of George Price. Some of you may be aware that my study organism are small amphipod crustaceans that live on sandy beaches. One of the fun things about working on beaches is that you never know what you're going to find. The ocean is constantly depositing its contents, living and otherwise, on the shoreline. During the summer and spring months on the Texas coast, we'd often find hundreds of Portuguese man-o'-wars, these gorgeous blue and purple siphonophores related to jellyfish, infamous for having a nasty sting washed up onto the beach. These organisms are not really a single organism at all, but a dense colony of individual polyps. That is, what we call Physalia physalia is actually many individuals that have aggregated together. Each individual has a task. There's a kind of division of labor. Some are what we call dactylozoids. These are individuals specialized for stinging and capturing prey. Others become gastrozoids. These actually ingest the food and digest them. Some even become part of the nematophore. This is the air-filled sac that allows the man-o'-war to float on the surface of the water. Some of the individuals, however, are lucky enough to become the gonozoids. These are the ones that actually produce gametes. Hence, they are the only individuals in this complex colony structure that get to reproduce. This creates a kind of Darwinian quandary. You see, natural selection acts to favor traits that increase an individual's reproductive success, but colonial animals, like the man-o'-war, is composed of individuals that mostly don't reproduce. They voluntarily sacrifice their own reproduction to serve other tasks in the colony. Now, obviously, if they stopped doing their jobs, the gonozoids would have no food or ability to stay afloat, and the entire colony would die. So it's essential these non-reproducing individuals do their jobs. But how could this structure ever evolve in the first place? A similar example is in the case of the amoeboid dictyostelium, commonly called slime molds. Most of their lives, these single-celled eukaryotes live as solitary individuals, feeding on bacteria in the soil. But if the conditions become dry or the food resources depleted, these solitary individuals will congregate with others and congeal into a kind of slug. Then, the top half of the slug elongates to form a stalk, and the bottom ascend the stalk and amass into a colorful bulb. These individuals become spores that then disperse to new locations that might be more favorable. What happens to the stalk? They all die. Some 20 to 50% of the original individuals of the slime mold sacrifice themselves for the good of others. Humans have always been fascinated by altruism. We have hundreds of tales of heroes willingly sacrificing themselves for the good of others. There's this favorite scene of mine from the silly movie Independence Day, starring Will Smith and Jeff Goldblum, in which one of the fighter pilots flies his ship into the alien spacecraft, sacrificing himself to save mankind from the invaders. Perhaps more serious of a story is that of Jesus Christ. To absolve mankind of its sins, he sacrifices himself in the ultimate act of altruism. To begin to understand George Price's curious life and incredible contribution to resolving this question of the evolution of altruism, it's perhaps instructive if we start at the end of it. Price died in 1975 and was buried in an unmarked grave in West Suffolk. Only about 10 people were at his funeral, and most of them were homeless people. But among the small gathering were two of the greatest minds in evolutionary biology: John Maynard Smith, who brought game theory to evolution, and W.D. Hamilton, called Bill by his friends, who introduced the concept of kin selection that would become known as Hamilton's rule. What were these two great evolutionary thinkers doing at the graveside of this obscure man among all these random homeless people that had also gathered in mourning? In 2016, George's daughters finally had a headstone added to the plot that will provide us with some hints. It reads, George Robert Price, 16th of October, 1922 to the 5th of January, 1975. Father, altruist, friend. Brilliant scientist noted for the Price equation for evolution. The word altruist on George's headstone immediately jumps out at us. While this epitaph wouldn't have been present in 1975, the attribution of this trait to George would have been familiar to Maynard Smith and Bill Hamilton. And beyond this, each of these men spent large portions of their careers investigating the evolution of seemingly paradoxical traits such as altruism. And so here, on a cold day in January of 1975, these British men who had studied the evolution of altruism stood in mourning of their American friend George, the altruist. Despite the occasion, Bill and Maynard Smith likely exchanged no words. Ironically, though each were interested in the evolution of what could be called the ultimate kindness, they were bitter enemies with no kindness for one another. Questions over the evolution of altruism originate with Charles Darwin himself. Upon observing the unique mating structure of eusocial insects, especially certain wasps, bees, and ants, he remarked that they represented a special difficulty for his theory of natural selection. As with the siphonophore and the slime mold, why would most individuals of a hive sacrifice their own reproduction? Indeed, even sacrifice their own lives, as many bees die upon stinging in defense of the hive. In The Origin of Species, Darwin considered worker ants and bees akin to somatic tissue, and the hive as a kind of superorganism. Well, this explanation satisfied him with respect to simple reproduction and non-reproductive individuals. What baffled him was how variation could emerge among the non-reproductive individuals. For example, in some ant colonies, there exist large defensive soldier ants that protect and fight for the colony, while there are other smaller worker ants that care for the larvae. why would one non-reproductive persist in a more dangerous role if it didn't increase its own reproductive success? Darwin explained this by invoking selection at higher levels of biological organization. For example, if we imagine a population subdivided into groups and one of those groups has soldiers while the others don't, then the group may be better able to defend itself than other groups, though individuals within that group, namely the soldiers themselves, suffer high casualty. Hence, the group itself leaves more copies in the next generation. One group becomes 2, then 4, etc. This idea became known as group selection, and it was hotly contested throughout the first half of the 20th century. It was perceived as a way to explain many oddities in nature. For example, why do organisms senesce? Why not live forever? Group selectionists argued that growing old and dying was itself favored so that their offspring could grow and reproduce. If the previous generation didn't die, they'd deplete the resources for each successive generation, and eventually the species would go extinct. This explanation relies on selection favoring death at the group level, since death at the individual level necessarily reduces fitness. So groups, or species, that never senesce are disfavored because not dying decreases the ability of the group to persist. Mathematical population geneticists were highly skeptical. R.A. Fisher, in the second edition of the Genetical Theory of Natural Selection, argued that selection acting above the level of the individual is weak due to the increasingly fewer number of competitors. That is, the efficiency of selection is dictated by how many replicating units there are. If there are only 3 groups, but thousands of individuals per group, selection will be completely driven by reproduction and competition at the individual level, since there exist far more individual replicators than group replicators. Sewell Wright showed the same thing mathematically in 1948, that group selection would be inefficient to counter selection acting on individuals within the group. J.B.S. Haldane suggested that if the population was sufficiently divided into many groups, and that altruistic behavior reached high frequency in some of them, such that the group could be considered as a consistent and faithful replicator of altruism, then it could spread. Interestingly, Haldane might have had an intuition about how to resolve this problem despite never formally offering it. Maynard Smith, who was a graduate student of Haldane's, has remarked that Haldane once said that he would, quote, lay down his life for 2 brothers or 8 cousins. What did he mean by this? Recall that there's a 50% chance that you share the same genes with your sibling. So, if you die while 2 of your siblings live, you have a near 100% chance that your genes still persist in one of your surviving siblings. Similarly, there's only a 12.5% chance you share the same genes with a cousin. To get that number to 100%, you'd need to save at least 8 cousins. In this throwaway line by Haldane, we see the first indication of how to resolve this issue of altruism. Bill Hamilton, in a letter to the editor of the American Naturalist in 1963, proposed that the probability of an altruistic trait emerging was a function of the cost of the trait to the individual altruist and the benefit that it provided to others multiplied by the level of relatedness between the altruist and the benefactor. That is, altruism is more likely to evolve between close relatives than it is between very distant relatives. Hamilton writes, quote, a gene causing altruistic behavior towards brothers and sisters will be selected only if the behavior and the circumstances are generally such that the gain is more than twice the loss. We can express this simply as R is relatedness, B is the benefit, and C is the cost. For altruism to evolve, R multiplied by B must be greater than C. Between siblings, R equals 0.5, so if the cost is 0.25, the benefit must be greater than 0.5 for the inequality to be satisfied and the trait to evolve. This has since become known as Hamilton's rule. The 1963 letter to the editor was just over a page long and presented a very crude model that was mostly verbal. For a complete treatment, Bill submitted a hefty manuscript to the Journal of Theoretical Biology later in 1963 that included a complete mathematical derivation and extensive remarks on the natural history of altruism, including how his model could explain the evolution of eusociality in insects. The mathematics in the manuscript were obscure, with odd notations that baffled the reviewers. The editor sent the paper to Maynard Smith for his input. According to Maynard Smith, this was the first time he became familiar with Bill Hamilton. But Bill had already acquired some disdain for Maynard Smith prior to his serving as a reviewer on his manuscript. Both Bill and Maynard Smith were at the University College London at the same time in the 1950s, where Bill was a student of the mathematical geneticist and statistician Cedric Smith. Maynard Smith was already an established professor and had expressed interest in behavioral evolution, especially with respect to modeling it mathematically. Bill recalls in his memoirs meeting Maynard Smith during this time when he was a graduate student. In his telling, Maynard Smith was cold to him and showed no interest in helping him with his work, despite the fact that Bill and Maynard were both working on the same problems. Bill Hamilton was a person who never forgot a snub. He internalized every insult, brooding over them incessantly. Indeed, while Bill was deeply hurt by Maynard Smith's coldness towards him, Maynard Smith himself later recalled never even remembering meeting Bill prior to seeing his manuscript in '63. As Bill was working on his '63 manuscripts, the debate over group selection was reaching a fever pitch. An English zoologist named Vero Copner Wine Edwards published an influential book on group selection in 1962 titled Animal Dispersion in Relation to Social Behavior. This book would have almost certainly been on the minds of both Bill Hamilton and Maynard Smith, and upon receiving Bill's manuscript to review, Maynard Smith would have immediately seen its relevance to the debate on group selection. Now, your feeling about what happens next is a matter of interpretations and motivations. Maynard Smith recommended that Bill split the manuscript into two parts, the first dealing with the mathematical treatment, and the second the application to the evolution of behavioral traits. While Bill was working on this revision, Maynard Smith published an article in Nature titled Group Selection and Kin Selection. The paper was aimed at Wine Edwards' 1962 book on group selection, and it argued that the concept of inclusive fitness was a better explanation for the emergence of altruism. Inclusive fitness he defined as an individual's fitness plus the fitness of relatives that carry the same genes they do. Hence, kin selection acted on inclusive fitness, favoring families that help each other over those that don't, so long as the cost of helping doesn't exceed the inclusive fitness gains. To Bill Hamilton, Maynard Smith had stalled the publication of his manuscript so that he could preemptively publish on the topic and introduce his own terminology, inclusive fitness, to explain what was essentially Bill's idea. And since Maynard Smith's article appeared in 1964, we know that he would have already read and reviewed Bill's manuscript and been familiar with the arguments. Perhaps justifiably so, Bill was furious. For Maynard Smith, the splitting of the manuscript was not malicious, but seen as a way to help promote what he thought was an important idea. He argued that if Bill published it as a single paper, most people wouldn't get beyond the obscure math to see the important applications. Hence, by splitting it up, one paper could be targeted for the more theoretically minded, and the other to the natural historian. Obviously, it's impossible to resolve motivations, but it's fairly easy to see why Bill, who already harbored some animosity towards Maynard Smith, would conclude that Maynard Smith acted out of his own self-interest by stalling Bill's manuscript publication. Regardless, the Journal of Theoretical Biology would later that year publish the two parts of Bill's manuscript, the Genetical Evolution of Social Behavior, Parts 1 and 2. This work has been interpreted over the years as a triumph of Darwinian thought, especially the gene-centric view of evolution. Richard Dawkins has referred to Bill Hamilton as the greatest Darwinian since Darwin. By dispensing with the notion of the group, Bill refocused the attention on the gene. What matters is relatedness, not the survival of groups or species. In the end, altruism is not about the greater good at all. It's nepotism. It's the selfish gene sacrificing its vehicle to ensure other copies of itself persist. Now, the self-sacrificing acts of the slime mold make sense. It turns out all the members of the motile slug are clones of one another. In fact, if you experimentally force the mold to include non-related individuals, they'll kill each other. Similarly, the individual polyps of the Portuguese man-o-war are clones as well. In eusocial wasp, there exists what's called a haploid-diploid system, in which all the males are haploid, being born from an unfertilized egg, and all the females are diploid and come from fertilized eggs. Hence, offspring are 100% of their father and 50% of their mother, meaning that they are actually more related to their sisters, including the queen, 75% relatedness to one another, than they would be to their own offspring, only 50%. This extreme system means that it is actually a fitness advantage under Bill's system of kin selection for sisters to abandon reproduction entirely and promote the reproduction of the queen than it would be to have their own offspring. In fact, Bill argued that haploid-diploid systems always lead, inevitably, to eusociality. In 1966, the great American biologist George C. Williams published Adaptation in Natural Selection, which served as a proverbial nail in the coffin for the traditional concept of group selection. Williams was a fervent critic of group selection, once saying to himself, quote, "If this was evolutionary biology, I wanted to do something else, like car insurance." In his 1966 book, he argued forcefully that selection acts on individuals or genes, not on groups or species. This controversy may have died then, if not for a letter that Bill Hamilton received in 1968 by a man he'd never heard of requesting reprints of his 64 papers. The letter started, quote, "I have just been reading your very interesting paper on the genetical evolution of social behavior, and was curious if Bill was aware of any evidence that enabled relatives to detect if they were sharing the exact same gene copies." While the letter writer stressed that this might be far-fetched in other species, perhaps in humans, quote, "some interesting effects could, in theory, occur." The man was George Price. Bill responded that he no longer had any reprints of the 64 papers, but he sent a 67 paper on the evolution of sex ratios, which touched on some of the topics that this George Price was interested in. With respect to whether or not individuals could recognize relatives genetically, Bill wrote back, quote, "So far I haven't arrived at any clear idea even as to what sort of game the genes are expected to be playing when operating together." He went on, quote, "I am sure that prisoner's dilemma situations are common and important in biological evolution." The prisoner's dilemma was introduced in 1950 by mathematicians Merrill Flood and Melvin Drescher, and served as a kind of thought experiment in which two individuals must choose whether to cooperate for mutual gain or betray one another for individual reward. In the language of animal behavior, animals must choose to either cooperate or be selfish, spiteful, or altruistic. This offhand comment by Bill Hamilton in his letter to this man he'd never heard of had major ripple effects across the field of evolutionary biology, and it would drag Maynard Smith into association with this enigmatic character, George Price. Instead of a letter, Maynard Smith first heard of George Price in the same way he heard of Bill Hamilton, or at least first remembered hearing of him. He received a manuscript to review. This was late 1968, after Price had read Bill's letter and had been struck by the idea that genes were playing games, and that perhaps the notion of the prisoner's dilemma could be extended to animal behavior. The manuscript Maynard Smith received was 50 pages long and submitted to the journal Nature, which famously only publishes very short manuscripts. The manuscript was titled Antlers, Intraspecific Combat, and Altruism. In it, Price argued that one can imagine male deer interacting in a sort of cost-benefit matrix, and variation in certain abilities, such as the ability to fight or de-escalate a fight. Further, there was a cost to fighting, and the cost-benefit ratio depended on the context of the interaction. For example, individuals defending a territory had more to lose, and so should fight harder than those without a territory and trying to take one. Price further suggested that the evolution of antlers served to protect against harm and ultimately to limit combat entirely, transferring all aggression into display. In this way, the total cost of fighting would be minimized. While Price's argument was wholly verbal, he had stumbled on the concept of evolutionary stable strategies, behaviors that persist in equilibrium with others, assuming that your opponent is a rational interlocutor. Maynard Smith was very impressed and recommended that the article be published, but that it would need to be shortened considerably. Inspired by Price's manuscript, Maynard Smith would turn his own mathematical skills to game theory, and in 1982 would write the famous book Evolution and the Theory of Games. These two events, a letter to Bill and a manuscript review to Maynard Smith, would inexplicably tie these two great evolutionary biologists to George Price. But just who is this enigmatic man who found himself at the center of the group selection, kin selection controversy? And just what is the famous Price equation that is etched on his tombstone? George Price was born in New York in 1922, the son of an electrician and a failed actress who had met one another on the set of a theatrical play. His father died when he was only 4, and his family spent much of the 1930s struggling through the Great Depression, as so many did in that decade. Nevertheless, Price would earn a degree in chemistry from the University of Chicago. His friends have remarked that he was strange, rambunctious, loved attention and pranks, was annoyingly contrarian, and some wondered whether or not he was, quote, a little nuts. While working on his graduate degree, he was employed as part of the Manhattan Project, which was working to develop the atomic bomb during the Second World War. As a chemist, he was investigating the radioactivity of the plutonium-235 isotope. While working on the project, he met Julia Madigan, the daughter of Jewish and Irish immigrants. In many respects, they were polar opposites. Julia was a devout Roman Catholic, he was a fervent atheist. She was against the bomb they were building, he was in favor of it. She was reserved and prudish, and he was extravagant, obsessed over and openly discussed sex. And despite these differences, he fell quickly and madly in love with her. But there was a strange transition in George after the war, and by the time he and Julia were married in 1947, his friends remarked that he had become withdrawn, disinterested, and was, quote, a loner who kept to himself. He played chess to pass the time because he was otherwise just depressed and bored of his work at the university. He lectured in chemistry at Harvard for a short time after receiving his PhD from UChicago, but quickly became interested in a completely different subject. In 1948, Claude Shannon had published his General Theory of Information, which utilized mathematics to quantify information content. George was fascinated, and so he decided to apply to work at Bell Labs, where Shannon was, and moved his family to New Jersey. By 1949, he had a small home in Jersey, a wife, 2 daughters, and a fancy job at Bell Labs. In the post-war America, this was the definition of the American dream. But George and Julia were fighting incessantly. His quirky attitude and demeanor was tiresome, and he would make extreme comments about Julia's religion, including that he'd rather their daughters become prostitutes than nuns. Perhaps in a vain hope that a change in scenery could salvage their marriage, George moved from Bell Labs to work at the University of Minnesota. He had gotten a job offer from his old boss on the Manhattan Project to work on radiation therapy and X-rays in diagnosing cancer. While there, George solved a series of mechanical riddles that prompted his boss to proclaim that he was, quote, one of the most remarkable individuals and clearly a man of genius. While his work was a success, his marriage was a failure. The marriage had become sexless. Understandable given that George's incessant teasing and hurtful comments to Julia, and this resulted in him seeking partners elsewhere. There are at least 2 documented affairs that occurred during this time. In 1953, he and Julia split, leaving her a single mother with 2 children. While the 1950s represented a time of rapid economic growth in the United States, it was also punctuated by Cold War hysteria driven partly by Senator Joseph McCarthy. Dragged alongside these paranoid fears was this widespread embracing of parapsychology, a pseudoscience field that supposedly investigated the sixth sense. It was promoted by Joseph Rhine and Samuel Soule, the former a botanist by training, and the latter a mathematician who, initially skeptical of Rhine, became wholly convinced that some individuals were capable of violating the laws of physics. It initially might strike one as curious that George Price would ever get involved in a furious battle with a group of parapsychologists, but it helps to note that his mother, Alice, had become convinced that she could communicate with the dead. She would write letters to herself in her dead husband's hand. Whether driven by his mother's obsession with the topic or genuine concern that Rhine and Soule were doing real harm, he wrote 2 articles in the journal Science criticizing the new fad. One titled Science and the Supernatural in 55, and the second, Where is the Definitive Experiment in 56. The articles led to thousands of readers sending letters to the New York Times, who covered the article with the headline, "Researcher Devotes His Life to Science." Some praised Price, some were outraged. The publicity was so great that Science decided in 1956 to dedicate an entire issue to the back and forth between Price, Rhine, and Soule. The articles are mostly angry diatribes against one another, and it's unclear that the entire affair actually changed anyone's mind. He found for a time science journalism suited him, and so he penned numerous articles for the magazine Popular Science Monthly, and even wrote profiles on Claude Shannon and the geneticist Herman Mueller for IBM's magazine Think. He also wrote an article for the magazine Life titled "The Case for Being Panicky" that argued that the United States should view the Russian satellite Sputnik as a warning to step up missile production. George grew increasingly fascinated by the Cold War, and on the merits of his Life article won a contract with Harper & Brothers to write a book on the Cold War. After seeing the drafts of the book, titled No Easy Way, Harper rescinded the contract, stating that the book was unsellable. In 1958, he managed to get a contract with Doubleday, who wanted the book ready in no more than 3 months. While all of this may sound like success, George Price was beginning to spiral. He was quickly running out of money, having left his job in Minnesota to work in New York City full-time as a journalist, and his ex-wife Julia was demanding that he pay alimony to help support their daughters. With the Doubleday agents breathing down his neck, he began popping pills, barbiturates, psychostimulants, ephedrine, whatever he could get his hands on. He wrote that, quote, he spent most of the day so far lying down, that the drugs removed his panic, but also every other emotion that he had. He felt numb and empty. In 1960, a non-malignant tumor was found in his thyroid. The tumor was successfully removed, but George suffered from a thyroid imbalance as an outcome, and so was given thyroxine pills, a new treatment for aiding hormonal imbalances. In 1961, George wrote to Doubleday and told them that the book No Easy Way would have to be set aside. He later complained that the, quote, world kept changing faster than I could write about it. Instead, he took a job at IBM as a consultant. While at IBM, George was given incredible leeway to work on his own schedule, which often meant he worked from home, appearing in the office sporadically, and this caused many of his co-workers to be skeptical of him. No one was sure what his role was. Was he a chemist, a journalist, an engineer, a medical researcher? What was he doing now in computers? He worked on optimization criteria at IBM, but then he quickly became obsessed with other things. During that time, he started devouring papers on retinal microanatomy and claimed that he had discovered the role that glial cells have in vision. He sent his work to John Eccles, a Nobel laureate in physiology, who politely responded that the paper was remarkable, but that he couldn't really follow the argument. He wrote, quote, your physical treatment of this important problem is beyond my mediocre attainments. In 1966, he was diagnosed with thyroid cancer. he decided to go to an old friend, Don Ferguson, for the operation. While the cancer was successfully removed, the operation was a disaster. George was left partially paralyzed in his left arm and face, and he was devastated. He wrote to a friend, quote, "I wish he," meaning Ferguson, "would go to someone for a hernia repair and have his penis de-innervated." He began referring to the surgery as a, quote, butchery. George began to spiral into depression. He even contemplated murdering Ferguson in several of his letters. Doubleday now demanded that he return his $2,500 advance for the book that he'd never written. His ex-wife still needed money for the children and to help pay the bills for their daughter Kathleen's private school. He started neglecting his medication, which led to increased hormonal imbalance, which only exacerbated his depression. He was admitted for a short time into the Payne Whitney Psychiatric Clinic, where he partially recovered. The only positive to come out of the botched surgery was that the insurance paid him handsomely. So he decided to quit his job at IBM. He told his friends that he had decided to take some time and to write papers on, quote, the evolutionary origin of a number of the peculiarities of human anatomy, physiology, and behavior. He wrote to his daughters that he was going to go to Europe to write some articles for a time. On November 13th, 1967, he sailed aboard the Queen Elizabeth to England, already on his mind the problem of altruism. He would never return. I often wonder what was going through George Price's mind that would prompt him to drop everything and move to London. He had a steady job, making decent money at IBM, and despite the botched surgery, now had a hefty insurance settlement that could permit him to live comfortably. Instead, he moves across the Atlantic to a place where he knows no one at all to live in a tiny, cramped flat in London. He wrote to one of his exes back home that he, quote, continued to be antisocial and that he still burned with a flame of hatred for Ferguson. He wrote to his agents at Doubleday that he, quote, would not live for more than a rather small number of additional years, and perhaps for quite a bit less, depending upon how things go during the next year. Today, this sort of language would have been cause for serious concern and perhaps prompted medical intervention. But in the 1960s, it went unreported. London was alive with protests of the Vietnam War, but George spent his time in the library at the University College London reading furiously. When the library would close, he would hurry over to Holborn Public, which stayed open later. He read everything he could about anthropology, population genetics, behavior, psychology, etc. And it was during this time that he came across Bill Hamilton's papers on kin selection. George embarked on two major projects in 1968 during his first full year in London, both inspired by his correspondences with Bill Hamilton. The first was his paper applying the logic of game theory to the evolution of antlers, which resulted in the 50-page manuscript he submitted to Nature that would ultimately find its way onto the desk of John Maynard Smith. The second was his obsession with the concept of group selection and kin selection. He was deeply impressed by Bill's work. In the 1964 paper, Bill had argued that altruism evolved due to the probability of being related, and hence strongly constrained by ancestry. In addition, it seemed impossible that altruism's opposite, spite, could evolve. In a biological context, spite is harming oneself to harm another even more. An example of this occurs in the flower beetle Tribolium. An allele exists called Medea, named for the Greek princess who murders both her brother and her children. When an individual is heterozygous for Medea, any offspring that don't possess the allele are killed. This seems like a clearly deleterious allele, unless you consider that it is simply a selfish, spiteful one. By killing any gamete that doesn't possess the allele, it ensures that it always increases in frequency in the population, even if it does so at the cost of the number of individuals within the population. The 1964 derivation, RB greater than C, was incapable of modeling spite because as relatedness decreased, there was no way that the benefit could overwhelm the cost. To George Price, that meant something was missing, as it seemed like there were several examples in nature, like the flower beetle, in which spite existed. So George Price sat down and tried to come up with a simple mathematical expression that could explain kin selection in a way different from Bill's derivation that might allow spite and perhaps even multi-level selection to exist. To understand the Price equation, we need to take a step back and recognize that there are two ways to model nature. If you're familiar with my Causes of Evolution series, you've seen one such way. Start with a series of simplifying assumptions and then, piece by piece, construct a model based on how we think reality works. Maynard Smith referred to these as microscopic models. These are models interested in reducing all the complexity of reality down to just a few simple parts. This is intuitive and powerful, but it leads to uncertainties about how the various assumptions of our models are influencing our results. Indeed, we often aren't even sure of the relationships between each of the assumptions when we construct models in this way. Nevertheless, this is how many models in science are built. In physics, we have models of ideal gases. In engineering, there are frictionless pulleys, and even the notion from economics that consumers are rational. All of these are simplifying assumptions necessary to construct simple models of reality. But there is another way. Instead of starting with assumptions, we could start with the system itself and ask if we can represent the component parts of the system mathematically. So let's now derive the Price equation, the most general and fundamental theorem of evolutionary theory, from which all subsequent theorems can be derived. We'll start with a little bit of necessary background into means, variances, and covariances, and then we'll derive the theorem. After that, we'll show how one other theorem, the famous fundamental theorem of natural selection, can also be straightforwardly derived from the Price equation. So, buckle up and let's derive the fundamental theorem of evolution. Okay, so to understand the Price equation, we're going to need just a little bit of background first. To do this, I started off by simulating some data, and then we're going to use that simulated data to try to learn a little bit about things like means, variances, and covariances. I know, very exciting stuff, but it's important, and you won't understand the Price equation if you don't have a good conception of these ideas. So I'm using the syntax from the R programming language, if you're familiar with that. If you're not, it's fine. I'm going to walk you through it anyway. So first thing, I created an object that we'll call X, which is 1,000 draws from a random normal distribution with a mean of 5. And then when you plot that as a histogram, that gives you this plot here. So these are the frequency on the y-axis, and then the trait or the x value on the x-axis. And then I've just drawn this red line that represents the mean value of 5, and then you get this kind of bell curve around it. Okay, so the x object that I simulated is a vector of n values, with n being the total number of draws, which we can show as x is equal to x1, so the first x value, x2, the second x value, all the way to xn. These little subscripts, these are what you call indexing. So this then tells you this is the first x value, this is the second x value, all the way to the last one. Okay, so whenever you see these little subscripts, these are telling you that these are just indexing the values such that the total x is actually composed of all of these other values within it. We can then take the arithmetic mean of our object x, which again is a vector, and whenever you see the bar over a value, so like this is x, the way you read this is x bar, this is telling you that this is the mean of the vector x, which you can write as x1 plus x2 all the way to xn, so summing all of the values in that vector, and then dividing those values by the total number of indexes. So from 1 to n, that represents the total number of indexes. And this is the arithmetic mean that you're all very familiar with. There's a couple of ways to write this arithmetic mean that's very important and is going to help us to see what we call identities when we start deriving the Price equation. So x bar, again, is the mean. You can also write as equal to 1 on n multiplied by this summation term. Now, just in case you're not familiar, let's explain what the summation term represents or how to read it. So the bottom tells you where to start, the top tells you where to end. So from I is equal to 1, so that's the first index, so traditionally we use I as for the index, equals 1, so that's the first x1, all the way to n, that's the x of sub n. All right, so that's telling us sum across all values from I equals 1 to n. And the sum, and the values that we're summing are x and then the subscript, so whatever the index is. So again, this is just telling us to do this operation, to sum x1, x2, all the way to xn. So this little term here is telling us to do the exact same thing that this term is telling us to do. Now, another way that we can write this is as an expectation, which is traditionally written as E parentheses with the x inside of it. We call this an expectation because if you draw values at random from this vector, we expect on average to get the mean value, right? So we can write the mean simply as the expectation of x. Whenever you plug this into the R programming language, you can use the function mean of x, that's just of the vector I simulated, and it's equal to 5.02. Which is very close to the mean that I actually told it to give. Okay, so that's the mean. We should all be pretty familiar with means, and the next thing that we need to understand is the variance around that mean. So this actually dictates the width of the curve itself, right? So this is the curve that I simulated. You can see that this curve has some width, and that width is defined by the variance. So we write this as the variance of x, so var x is equal to 1 on n, the sum from I equals 1 to n of x sub I minus x bar squared. Okay, so this is x sub I, this is the first x value minus the mean squared plus the second x value minus the mean squared. And then you do this for all x values until you get to x sub n. All right, and then that term represents the variance. And in our case, in the simulated object I did, it's equal to 0.969. So almost equal to 1. And you can see down here on the x-axis, this is 4 to 5. So this is a stretch of 1. And that is why the blue line is here. So that just represents the variance around that mean is right around 1. Larger variances just spread that distribution out. Narrower variances or smaller variances shrink that distribution towards the mean. Okay, so the next thing we need to talk about are covariances. A covariance relies on two terms. So if you have one vector x, and then you have another vector, which we can call y, and then we're asking for each one of those values in the vector, how do they vary with one another? So for every change in x, what kind of change in y do we expect to see? So to get this, I simulated an additional object, y, which is again random, draws from a normal distribution, mean of 5. But here I specified that the standard deviation was 3. So it's 2 times bigger than or 3 times bigger than the standard deviation from the x value. I haven't talked about what standard deviation is. The standard deviation is just the square root of the variance. Okay, that's all that is. So they are comparable to one another. So a large standard deviation also means a large variance. And you can see that here. So this is the histogram. You can see the mean is still around 5, but notice that the variance is much larger. So instead of being simply from just a variance of 1, the variance is actually quite large here. Okay, so what then is the covariance between x and y? So for change in x, what is the change expected to see in y? To write that, traditionally we would write covariance of x and y is equal to 1 on n, and then the sum from I equals 1 to n of x sub I minus x bar multiplied by y sub I minus y bar. Again, the i's are just indexes, so that's the first term of x, and then the first term of y, and then you do the second term of x and the second term of y, third term of x, third term of y, all the way to n. And that gives you the covariance between the two vectors x and y. Now notice I simulated these two vectors completely independently of one another, right? So there's not actually a causal relationship between these two. Nevertheless, even two randomly independent vectors can still have some positive or some non-zero covariance. So if you just calculate the covariance of x and y in R, it's equal to 0.054. I'm showing the relationship down here on the bottom. This is the relationship between x and y. You can see it's pretty much just smattered across it because they aren't causally related. But nevertheless, there is a positive covariance between them, and you can see a slightly positive slope. It's very hard to see it here, but the slope is technically slightly positive. Importantly, covariance is distinct from correlation. So correlation is the strength of the relationship between x and y, whereas covariance is the actual covariation between the two. So correlation ranges from -1 to 1, so it has a very hard upper and lower bound, whereas covariance has a maximum value of the square root of the product of the variance of x and the variance of y. This means, importantly, that if one of your vectors has a very large variance, you can increase the covariance between two terms, right? And again, even if they're random. So I did that down here, so I created another vector z, that has a much larger variance here. And you can see now the covariance between x and z is actually of a greater magnitude, 0.09, as opposed to the magnitude between x and y, which is only 0.05. It's negative, which just means that for every change in x, you get a negative change in z in this case. But it's the magnitude of change that we're actually interested in here. So again, by just increasing the variance in each one of those terms, you can actually increase the covariance between two random terms. This might seem a little obscure right now, but it's going to be important later on. Okay, so now we've talked about means, variances, and covariances. The next thing we need to talk about to kind of build up our background is the concept of regression. A linear regression is basically a line that is drawn through a series of points such that it minimizes the distance between each point. Okay, and then whatever distance actually exists between that line and all the subsequent points across the plot are what are called the residual variance. Okay, and that line, whatever that best fit line is, we often call the beta regression coefficient. And the beta regression coefficient turns out to be equal to the covariance between the two values divided by the variance in one of those values. So for the beta coefficient of yx, that is equal to the covariance between x and y divided by the variance of x. So effectively, what a linear regression is doing is it's telling us how much do these two values vary as a ratio of the amount of variation in the x value. And so when we put this into R, we get a covariance xy divided by the variance of x. That gives us 0.055. That is the best fit line. Now remember, as I said, it's very near zero, right? Very, very small line. And that's what this is showing us, right? It's a very, very small line. You can, just as a kind of sanity check, you can also run technically the linear model in R is just LM. That's the function of y on x. And then you use the function summary of that linear model, and that gives you this sort of breakdown of the different estimates, standard error, t-value, p-value, etc. This term here that I've highlighted in red is what we actually care about. This is the beta coefficient. And you can see it's equal to 0.055. So it's equal to the same thing that we got when we just took the ratio of the covariance to the variance. Okay, now this also tells us something pretty cool in that we can also redefine covariance as equal to the beta regression coefficient multiplied by the variance in x, right? We can just rearrange this equation up here, and that gives us a new definition of covariance. And so in expectation, the covariance between x and y can be written as equal to the expectation of the product of x and y, of those two vectors, minus the mean product of those two vectors. Okay, so that was a little abstract. I want to kind of bring those concepts back into evolutionary biology before we move over into deriving the Price equation. So for this example, let's let y be equal to fitness. So the y axis here, let's say that they're equal to fitness, and then x is just some trait value, okay? Now, when we regress trait values against fitness, what we're actually looking at is the covariance between any given trait value and fitness. Hence, the beta regression coefficient against those two terms is what is telling us the strength and the direction of selection on a quantitative trait. A quantitative trait is just any trait that has continuous variation. So this one on the left here, this is for just the raw trait values on the x against fitness on the y. The best fit line that's defined by the beta regression coefficient is equal to 2.98. What that tells us is that every generation, selection can change the mean of this distribution by 2.98. And that is what we call directional selection. Directional selection specifically acts on the mean of trait values. Now, alternatively, we also have forms of selection that don't act on means, but instead act on variances. So we can also plot the variance of that trait value against fitness. And that's what we've done here on the right. So this is now variance on the x, the fitness value on the y, and now what that beta regression coefficient represents is whether we have no selection acting on the variance, or whether we have stabilizing or disruptive. Stabilizing selection acts to reduce the variance around the mean. And so in this case, the beta regression coefficient would be negative on the variance. For disruptive selection, you are trying to increase the variance around the mean. So the beta coefficient would be positive. And so in our simulated example here, we see that there's very strong directional selection acting on the mean, but the beta regression coefficient on the variance is very near 0. This means that we expect directional selection to be shifting the mean, but that the variance in that trait should stay roughly the same. Now, what this also tells us is that these two forces can be acting simultaneously. For example, you can have both directional selection as well as stabilizing selection. If you have a positive beta regression coefficient on the mean values, and then you also have a negative beta regression coefficient on the variance, then you have directional selection moving the mean, while simultaneously stabilizing selection is reducing the variance. Thinking about selection acting in this way also kind of helps us think about selection acting in multiple dimensions, which may seem counterintuitive in a simple trait, but if you think about something that's multidimensional like development, right, that has many different dimensions happening all at once that selection could be acting upon. In this way, selection is happening on various moments of the variance distribution. So in the first variance distribution, remember, it's x sub I minus x bar squared. In the second moment, it's to the third, it's cubed. The next moment, it's to the fourth, etc. So in every single one of those moments, you can plot that variance against fitness and see what is the beta regression coefficient against it. And this can tell us how selection can be happening in multiple dimensions in varying different ways. The last thing that's important to note from this figure is the concept of additive genetic variance. So additive genetic variance is the variance that is being captured by the linear regression, right? So again, this is a straight linear or additive regression from trait values onto fitness. And so everything that falls near or is well described by this additive variance is considered to be part of the additive genetic variation, and selection is acting upon it. However, there are values that could be falling way off of that additive line. So you might have some, in this one, this is pretty straight, but you could have, for example, somewhere in the middle, you could have dots way up here. The beta regression coefficient is still going to be a linear line, but there's some variance that's falling up here that selection is not acting on. This additional variance that is being captured by the residuals, remember the residual is the distance between the best fit line and each one of the other points that are falling off of that line. This residual variance captures what we call the dominance variance and the epistatic variance. These are the two other kinds of variances that could be acting on the trait. So instead of that trait being purely additive, where it's just like if you have X number of loci, you can just sum up all of those loci and get your trait value. You could also have some of those loci behaving epistatically or in a dominant or recessive fashion. In this case, this will skew that variance off of the linear regression curve, and it increases the residual variance between them. So again, selection is still acting on that additive genetic variance, whether or not there's dominance or epistasis. I just want to make that clear that when we're talking about the additive genetic variance, we're specifically talking about the variance that is well described and captured by the beta regression coefficient against trait values on the x and fitness on the y. Okay, so now with that background out of the way, we are ready to derive the Price equation.
We're going to start off really simple, and we're going to talk in very broad general terms. And we're going to do this on purpose because I want to show just how broadly applicable and general of a theorem the Price equation actually is. So let's look at this as a diagram first. So up here at the top, these represent our ancestors, okay? So each one of these ancestors are first indexed from 1 to n, just like we did with our x vector. So this is ancestor 1, 2, all the way to n. And then each one of these ancestors have some trait, and we'll call that trait phi. Now this can be an allele, it can be a genotype, it can be a simple complex trait, a behavior, doesn't matter what it is. All that matters is that individual, that it's some measurable quantity of that individual that they then pass on. And so we can see each one of them have a unique index. Now, then they have some number of descendants. Descendant here is important. Doesn't necessarily have to be a parent-offspring relationship. This can be any ancestor and any descendant, okay? From any number of generations removed, it doesn't matter. There's no specification for that here. So our first individual has some trait value that they pass on to their offspring. And then this first offspring now has that parental trait value plus this deviation from that trait value. And this deviation is unique to this offspring. So we have the subscript here that is now indexing this offspring as having the deviation from parent 1 to offspring 1. Alternatively, you have the trait value from parent 1 and offspring 2, which with the deviation parent 1, offspring 2. Okay, so each one of these offspring have unique indexes. Furthermore, we then can define an additional term, which we'll call W. This is traditionally fitness. And this is the number of descendants that this ancestor leaves. We do the same thing with the second individual. So this is the second individual. They have some offspring now with their trait, plus the deviation from this parent, which is delta sub 2, 1, indicating second individual or second ancestor, first offspring. Same thing here, second individual, second offspring. And you do that all the way to n. So this is our very simple diagram that basically captures the entirety of the Price equation. As you can see, there's not any assumptions here, right? The only thing that we're looking at is that there are some ancestors that have descendants. Ancestors have some traits that are correlated with their descendant traits with some deviation. That's it. Right, so it's a very simple representation of basically any evolving system follows this basic representation. Furthermore, I want to point out we've made no assumptions about mating structure, about population size. We've made no assumption about spatial structure. We've not even made any assumption about the form of inheritance, right? Like we've not specified that this is Mendelian inheritance. And this is a really important component of the Price equation, is that it can incorporate any form of inheritance. It doesn't make any assumptions about whether the inheritance is Mendelian, whether it's genetic or non-genetic. It could be epigenetic, it could be environmental, it could be cultural, it can be any form of inheritance, right? I've put down here a little key to help us sort of keep up with all the different terms that we've introduced here. Okay, so one of the things that evolution is interested in is the change in mean trait value between ancestors and descendants, right? And that is effectively evolution, right? It's the change in some sort of transmissible trait from one generation to the next or across many generations. How does that trait, whatever kind of trait it might be, how does it change through time? And we can represent this as a series of summations. Now this looks kind of ugly, but I'm going to walk you through what each of these things mean, and then you'll see it's not as complicated as it might look. So this represents the mean trait value in some future generation, which we just denoted as prime, okay? So this is mean phi prime, or phi bar prime, okay? And then let's break this down in two different parts. So on the top, you have a double summation. So let's start with the inner summation first. So the inner summation is from j equals 1 to w sub I. The j term here represents offspring. So these are the offspring we're talking about, from the first offspring here to the last offspring of individual I. So that would just be these two individuals in our simple example. And then you sum phi sub I plus delta sub ij. What this is telling us to do is add up all of these values for each one of the offspring of individual I, okay? Then what the second summation is telling us is to do that for all individuals, right? So from I equals 1 to n, so from all the ancestors, calculate the trait value across all descendants. That is all this double summation is telling you to do. Now, furthermore, we are dividing this by an additional summation from I equals 1 to n of w sub I. We should recognize that this is just the sum of all descendants. So w sub I, remember, this is the number of descendants. So this is saying number of descendants of individual I. So we can say this individual had 2, this individual had 2, all the way to the last individual. Sum up all the number of descendants they had, and that becomes our denominator. And so we should see this as effectively an arithmetic mean, right? You have the sum of all the descendant traits up here on the top divided by the sum of all descendants. And that is why this is equal to a mean value. So now let's look at the relationships between the summations to try to get some idea about some identities that are present in the Price equation. So let's start off by distributing this first summation into this first term, which is our trait value. And that's what this looks like here. So this is from j equals 1 to w sub I. So all of the descendants of individual I that have some trait value I, and then you're just going to sum those trait values up. Well, this is the same thing as saying, what is the trait value of individual I, and then multiply it by how many individuals there are. Right? Those two things are equivalent to each other. So we can rewrite this summation as simply w sub I phi sub I. Similarly, we can do the same thing with the second term. Since this delta sub ij multiplied by w sub I is just saying what is the average value of the deviation across all individuals. And so that's all we're doing here. So then we're converting this summation into w sub I, and then we're now converting this into a mean. So this is delta sub I bar. Now for this last summation, we have I equals 1 to n of w sub I. All this is telling us to do is for every single individual that is a descendant, what is the fitness value? So to get that, you can just multiply the number of individuals by the mean fitness value, right? So we can actually just rewrite this summation as just n multiplied by w bar. In doing that, we can now plug in these new relationships into our original equation and get something a little bit simpler. So now we still have phi sub bar prime is equal to 1 over n w bar. Notice all we've done here is we've taken the denominator and we've just moved it out front, okay? This should start to help us see the next identities, right, relative to what I showed before with the arithmetic mean and the covariances. So that's why we've just got to move that out front, multiplied by now just the outside summation, right? So you still have the outside summation here. We've just gotten rid of the inside summation. So the outside summation is I equals 1 to n. So for all ancestors of the product of w sub I phi sub I. So what is the product of the fitness of individual I and the trait of individual I, plus the summation from I equals 1 to n of the fitness of individual I and the mean deviation from parent to offspring or ancestor to descendant of individual I. Okay, so like I said, we should begin to recognize some additional identities here. And if we recall that the definition of expectation is simply equal to the mean, right? And now notice this here. So this first term is the summation of this product divided by the total number of individuals. The sum of the values divided by the number of values is the definition of the mean. And so we can actually write this first term as the expectation of the product of fitness and the trait value. Similarly, we can do the same thing with the second term because it is also the mean, and we can write it as the expectation of fitness multiplied by the mean deviation between ancestor and descendant. So we've not actually changed anything, right? We've not done any simplification or anything like that. We're just rewriting the terms. So the n and the summations, they're all still there. They're just now captured in this simpler term here. Now, additionally, recall the definition of covariance. So covariance, remember, is equal to the expectation of the product of x and y minus the mean product of x and y. We can then rewrite this for the expectation by just moving that mean product to the other side. And now expectation is equal to the covariance of x and y plus the mean product of x and y. So we're going to plug that in up here for this first term. So we're just going to expand this to the covariance of fitness and trait plus the product of mean fitness and the mean trait value. Notice now that we have in the numerator, we have this mean fitness, and then we also have mean fitness in the denominator. Since those are equivalent, that's just equal to 1, so we can get rid of that. We'll move this value to the outside to make it clearer, and that gives us this expression here, where we have the covariance of fitness and the trait, plus the expectation of the product of fitness and the trait deviation, plus the mean trait value. Now all we have to do is move that mean trait value to the other side, and what we get is the mean trait value in some future generation, which is the prime, subtracted by the mean trait value in the ancestor generation is equal to, traditionally written as delta phi bar. So that is the change in the mean trait value between ancestors and descendants is equal to 1 on W bar multiplied by the covariance between fitness and the trait plus the expectation of the product of fitness and the trait deviation. And this, ladies and gentlemen, is the Price equation. It is the fundamental theorem of evolution. If you're a little lost in the weeds and you're not sure what this is telling you, let's walk through each one of these terms, and you're going to see that all of the processes of evolution are captured by this very simple and general theorem. Okay, so the first term is the covariance between fitness and a trait. Therefore, it's capturing differential survival and reproduction, and thus both natural selection as well as genetic drift. So think about it like this. If you have some trait, and that trait co-varies with fitness, such that as that trait increases, fitness increases. As that trait decreases, fitness decreases. Right? That's a covariation between those two terms. Hence, this term is capturing differential reproduction and survival. Now remember, as I showed before, you can also have a positive or negative, a non-zero covariance for terms that are actually randomly associated. So you could have some trait value that has no causal relationship to fitness, and yet they have covariance with one another. Hence, that's genetic drift. Therefore, both of those terms are captured by the very first term in the Price equation. That's pretty incredible, right? You've got natural selection and genetic drift. Two of the most important forces in evolution are captured by just a simple expression of the covariance between fitness and some trait. The second term is even wilder. So the second term represents deviations between the ancestor and descendant due to transmission. Now, this transmission could be mutations, it could be recombination, it could be segregation distortion, it could be gene conversion, or it could even be natural selection happening at different levels than what you're presently looking at, including things like gametic selection and possibly things like group selection, multi-level selection. So as we can see here, this term adequately captures all of the processes of evolution, from natural selection and genetic drift, from mutation and recombination, all of the various things that could be happening in populations of different sizes, of different transmission types, whether it's environmental, whether it's genetic, whether it's non-genetic, doesn't matter what. All of those terms, all of those different facets are beautifully captured in this incredibly simple and general theorem of evolution. So the last thing I want to touch on in our little derivation here of the Price equation is Fisher's fundamental theorem of natural selection. Fisher proposed this theorem in 1930 in his book, The Genetical Theory of Natural Selection. He did it in the most vague of ways, and for decades, people were utterly confused on what exactly he meant. Described it succinctly as the rate of increase in fitness of any organism at any time is equal to its genetic variance in fitness at that time. People have taken this to mean all kinds of things, including that fitness is always increasing, which seemed like it couldn't possibly be true, right? We have lots of stable populations, so how could fitness be perpetually increasing? We know that populations can go extinct, right? So obviously there's something missing in the traditional or classical understanding to Fisher's theorem. A theorem needs to be generally true all the time. So it's not much of a theorem if, a population can just go extinct and disprove your theorem, right? But our friend George Price actually uncovered in 1972 what Fisher really meant by the fundamental theorem of natural selection. And what we're going to show here is that we can actually derive Fisher's theorem straight from the Price equation, which means that it is indeed actually a general theorem of evolution. So I've put the Price equation up here at the top. Now all we need to do is treat fitness itself as a trait, right? So again, remember that trait can be anything. So let's set this trait value equal to fitness. Now what I'm doing here is I'm indexing the different W terms just so that we can keep them apart. So this is the fitness term for the ancestor. This is the fitness term for the descendant, okay? Just so that we can keep them apart. And again, this is the mean change in population fitness over here, okay? So now we can just apply the definition of covariance to that second term, right? And that gives us the covariance of ancestral fitness and the deviation plus the products of the two expectations. Now recognizing that the expectation here is just the mean fitness of the ancestor, which is in the denominator as well, so we can get rid of those terms. And then we can add in these two covariances because we have the first term is shared, and then we just add the second term to the second one here. That leaves us this expression where now we have the covariance between fitness and then descendant fitness plus some deviation, some mean deviation. And then all we need to do is let this second term here be described by WO, where O is just for offspring. Let it be equal to W sub I plus some deviation. And that gives us this expression where we have the covariance in ancestor fitness and descendant fitness plus some deviation. Now, to make this a little bit clearer to Fisher's theorem, we can just replace this covariance with this sort of additive genetic variance term. So remember, this is again the beta regression coefficient multiplied by the variance in offspring fitness. This is the additive genetic variance. And we see that the additive genetic variance here is equal to the mean change in fitness here. Hence, the rate of increase in fitness of any organism at any time is equal to its additive, Fisher should have added additive, is equal to its additive genetic variance in fitness at that time. So here we are, very, very simple derivation straight from the Price equation. Since we can get Fisher's theorem from the Price equation, that means that Fisher's theorem actually is very general and very applicable to any evolving population. The people debate in the literature all the time what the significance of it is. That's a whole nother question, whether it's very significant or whether it's very useful, like if you actually are going to use it for something. That really doesn't matter here, right? It could be completely useless and still be a true general theorem of nature, and that is what we've shown here. Okay, so now we've derived the Price equation, and we've shown a second fundamental theorem of evolution that can be derived from the Price equation, and that is the famous and sometimes infamous Fisher's fundamental theorem of natural selection.
George thought the expression he derived was a tidy and instructive way of thinking about selection. Furthermore, it dispensed with relatedness and instead only focused on the covariance between a trait and fitness. It showed that spite could evolve, that is, the covariance could be negative. Furthermore, it elegantly showed that selection doesn't actually care about relatedness or whether populations lived in isolated groups. It only cares about the covariance between fitness and the trait itself. Such a general formula seemed to George too simple to have never been derived before. In late 1968, he made his way to the University College London and asked to speak to a mathematical geneticist. Price retells the story in a letter to Bill that year, which includes some, excuse the pun, priceless moments. He writes, quote, On further studying the mathematics, I found that I had a surprisingly simple equation to gene frequency change under selection. I didn't think such a simple thing could be new, so went to the Galton laboratory one day last September, went in to the departmental office and asked to speak to a mathematical geneticist. So I was taken to see Cedric Smith. He looked at my equation, said it was very pretty and he had never seen anything like it, asked what I was doing in London, and when he heard I was living on savings and was totally unaffiliated, I was given an honorary appointment. Unbeknownst to George, this mathematical geneticist was the same Cedric Smith that had served as Bill Hamilton's graduate advisor. Later in the letter, George informs Bill that he thinks Bill has made some errors with respect to kin selection given his new calculations. That is, that not only could spite evolve, but that selection is actually indifferent to the family structure. He writes, quote, "But I did want, in view of your friendly correspondence, because I respected your work and because everyone makes a mistake now and then, to publish in a way that would not embarrass you." Bill called George the next day, writing in his memoirs that George's voice was slightly squeaky and condescending. He told Bill that the equation was a surprise to me too, quite a miracle. He then asks Bill, quote, "Have you seen how my formula works for group selection?" The response by both Bill and Cedric Smith to George's equation must have been uplifting. He wrote to his aunt, quote, "I think it will be considered a very important piece of work. I wish my mother might have lived to see it." He submitted the paper, little over a page long, to the journal Nature, and then, just a month later, before hearing back from Nature, sent a longer one to Science. He wrote to his daughter, Anna Marie, telling her that it was just a preliminary communication, but that it was crucial in understanding the evolution of animal behavior. But he was crushed in February of 1970 when Nature and shortly after Science both rejected his papers. The editor of Nature, John Maddox, wrote that it was, quote, "too hard to understand," while the editors in Science stated it was too abstract and not obviously pertinent to any biological problem. However, in May of 1970, he received a letter from Bill Hamilton in which Bill wrote, quote, "I am enchanted with your formula. I really have a clearer picture of the selection process as a result. In its general form, I can see how we might use your formula to investigate group selection." This was pretty stunning, coming from the man who had almost single-handedly buried group selection less than 10 years prior. Bill was convinced to use George's equation to demonstrate how spite could evolve. He knew they just needed to get his formula published, and then other evolutionary biologists would see how powerful it is. So he devised a plan. He would submit his journal on the evolution of spite to Nature, and once it was accepted, he'd write to John Maddox and tell him that he'd be forced to withdraw the paper if they didn't also publish George's selection equation, because the paper relied on its formulation. By this time, Bill Hamilton was a big name in evolutionary biology, and any paper that he published with the journal was guaranteed to carry weight and generate citations for the journal. The plan worked. Maddox relented and published George's paper titled Selection and Covariance in November of 1970, and Bill's paper on spite titled Selfish and Spiteful Behavior in an Evolutionary Model in December. Bill used George's equation throughout, elegantly demonstrating how the covariance term could permit negative values and hence the evolution of purposefully harmful behavior. While professionally, it seemed like George Price's life was looking up. He'd finally gotten his cherished selection equation published and see it applied to a question he'd long pondered, but George was slipping. He, now in his early 40s, became infatuated by a friend's daughter who was barely 18 years old, that he remarked shared both the name of an old girlfriend and looked remarkably like her, and that he had first met her exactly 13 years after meeting the ex-girlfriend. He wrote to this girl, whose name was Anne, that he, quote, wanted her very, very much. George began to see patterns everywhere, strange coincidences he couldn't make sense of. He pondered why his phone number, 580-2399, the last 4 digits he took to mean just before the stroke of midnight. never mind that it should have been 2359. He began poring through letters, notes, journals. He found patterns in the arrangement of letters, the numbers, everything. He started calculating all the strange coincidences of his life, that he, of all people who hadn't known, quote, a covariance from a coconut, would be the one to derive such a fundamental theorem of evolution. He wrote to his brother, quote, "I happened to notice one surprising coincidence in my life, and this started me searching back through my calendar books and letters and other materials and noticing a long line of succession of other improbabilities until the improbability level became astronomical. I listed long series of independent events having probabilities of the order of 1 out of 100 or 1 out of 1,000 that fitted together into a meaningful pattern, and when I multiplied these together, the product was something like I over I followed by 20 or 30 zeros." We know that George Price was using narcotics at this time, though the frequency is unclear. We also know that he was not consistent in his thyroxine medication, sometimes going weeks without taking it. Regardless, sometime in the summer of 1970, George Price had a complete mental break that shattered him irrevocably from reality. On June 14th, he walked into the nearest chapel, the All Souls Church, and gave his life to Jesus, becoming an avowed Christian. While this act itself is not the action of someone who has suffered a psychotic break, it is rather the actions that he took in his personal life following this that suggest that that was the case. He was sometimes seen afterwards running through the corridors of the University College London, screaming at the top of his lungs that he had a hotline to God. He wrote to his friends, including Bill Hamilton, that he had seen Jesus, that God spoke directly to him. He wrote to famous Christian pastors like Billy Graham and the creationist Henry Morris. In a bizarre correspondence with Morris, he wrote first that he had considered joining Morris's congregation, but that God told him not to. When Morris responded politely that he was sorry George wouldn't be joining, but that he was welcome to subscribe to their journal, George responded, quote, "You write, if you feel that you cannot join the society for reasons of certain items in our statement of belief. No, the reason that I do not apply for membership is that the Lord commanded me not to. It was not my choice, but His. I am sorry that you apparently did not understand that I really am a genuine slave and not like the usual evangelical Christian who prays for guidance and then makes his own decisions. I do not ask for guidance. I ask for commands, and then I obey them." Throughout 1971, George sent letters to Bill Hamilton asking him to review his novel and bizarre takes on theology. He had decided that Christians had Easter all wrong. It wasn't 8 days, but actually 12, and he designed a mathematical expression from Scripture to prove it. In the correspondences, Bill is always very gentle with George, but the concern seeps through. Even when George is being harsh, as he sometimes was, when Bill gently dismissed George's exegesis, preferring to discuss with him matters of science, George grew impatient, writing, quote, "I think better of you as a scientific thinker than as a wishful thinker, and wish you would drop this concern with aesthetics and concentrate on questions of scientific truth or error, as far as theological questions are concerned." That is, George was frustrated that Bill would not dedicate the same amount of time and effort to George's theological arguments as he was willing to do to his biological ones. During this time, George even sent a letter of apology to his old enemy Joseph Rhine, the parapsychology guru, but the correspondence quickly devolved to George lambasting Rhine for not turning to religion to explain his results instead of the paranormal. In 1972, George Price published his last 2 solo author papers, both of which appeared in the Annals of Human Genetics. The first extended his selection equation to include explicit interpretations of the transmission term that we talked about previously. In it, he used the controversial idea of group selection as an example of the application of his theorem. He showed that by simply indexing each of the covariance terms like we did individuals previously was akin to imagining different groups. Hence, his theorem included intergroup selection as well as intragroup selection. This hierarchical view of selection acting across different levels is one of the most powerful qualities of the Price equation. The second paper, titled Fisher's Fundamental Theorem of Natural Selection Made Clear, was not so much a feat of mathematics as one of interpreting the obscure writing of R.A. Fisher. Ever since Fisher proposed the fundamental theorem of natural selection in 1930, biologists have debated what it meant, how significant it was, and whether or not it was truly a theorem, as we talked about before. Fisher's theorem, as Price demonstrated and as we demonstrated in the previous chapter, is indeed a general theorem of any evolving population, but this was first uncovered by George Price. Price's personal life in 1972 began to merge with his professional. He'd spent the past 4 years obsessing over the evolution of altruism, how such a paradoxical trait could emerge via Darwinian processes. He'd found, as Bill Hamilton had before him, that it requires nepotism and spite. In the case of group selection, it wasn't sufficient that altruists helped each other, they needed to harm their neighbor as well. For kin selection, individuals only helped relatives because ultimately it was the genes and not the individual that persisted. But he'd had this miraculous conversion to Christianity, a religion built on the symbol of sacrifice and true altruism, not nepotism. How could he reconcile these two competing views of nature? As became George's way, he waited on a commandment from God, and in 1972, he received one. Jesus appeared before him, he'd later tell Bill Hamilton, and told him to give everything he had to the poor. George would become a living contradiction to his own work on the evolution of altruism. He started giving away money to every homeless person he could find, brought them food, invited them to live in his home. At any one time, George might have 6 or 7 homeless people sleeping in his tiny, cramped flat. Many of them stole from him, but he didn't care. He was not in it for himself. He was following God's commandment. This was the condition that Maynard Smith would find George Price in. Having returned from a short stint at the University of Chicago working on applying game theory to evolution, he'd returned to London and was ready to put together a manuscript on the computer simulations he'd been devising. Since he'd been inspired by George's Antlers manuscript, he wanted to cite it. But when searching back through issues of Nature, it seemed like it had never been published. He wrote to the journal to get George's address. In the summer of 1972, the two of them sat down and worked out the first known example of an evolutionary game. And in the manuscript that resulted in 1973, titled The Logic of Animal Conflict, introduced the idea of an evolutionary stable strategy, often shortened to an ESS. Let's walk through the most famous of evolutionary games, what Maynard Smith and George Price would call the hawk-dove game.
Okay, let's learn how the very simple hawk-dove game works. The name hawk-dove actually comes from the Vietnam era, where the hawks were the ones that wanted to fight and the doves were sort of the peaceful ones. And that can help you understand what these behavioral strategies are supposed to represent. Importantly, they're not hawks and doves, the animals, they are behavioral strategies, okay? You can think about bold and timid if that helps you separate these two things. The way the game works is it's a 2-player game and either player can play either of the two strategies, and then we kind of assume that each player is going to play the best strategy. We can set up this little cost-benefit contingency table, and what determines the best strategy is how much benefit you can get. You can think about it as the players are vying over a resource, and the different behavior that you employ depends on the interaction that you're having with another individual that also wants that resource, okay? So if two hawks come together and meet, which is this very first square here, then they're gonna fight over that resource. On average, they each get half of the resource, but they suffer some cost. So player 1 gets this B over 2, which is half of the resource, minus C, which is the injury that they suffered for fighting. Player 2 gets the same thing, b over 2 minus c. Now, if a hawk meets a dove, since doves never fight, then the hawk will get the full benefit. They take the whole resource and leave the dove with nothing. That's shown here. The b goes to player 1, the 0 goes to player 2. Same thing down here. If player 1 plays dove, they get 0. If player 1 plays hawk, they get the full resource. Now, if both players play dove, then they split the resource. Half goes to player 1, half goes to player 2. Now that we know the rules of the game, let's see if we can figure out what's the best strategy to play. So if player 1 plays hawk, what should player 2 play? Importantly, the information that we need to know what the rational choice is whether b over 2 minus c is greater than or less than 0. That is the cost to fighting greater than the benefit that you would get from fighting? Let's assume in this case that half of the benefit minus the cost is still greater than 0. Hence, what should player 2 play? Well, notice if player 2 plays hawk, then they still get something greater than 0. There's still some positive resource value that they're getting. If they play dove, however, they get nothing. There's no benefit that they could possibly get. And hence, hawks should always win when b over 2 minus c is greater than 0. It is never rational for player 2 to play dove if player 1 plays hawk. Hence, in this evolutionary game, the hawk strategy should sweep the fixation and the dove strategy should be purged from the population. Now let's assume the case in which b over 2 minus c is less than 0. That is, that the cost exceeds half of the benefit. So in this case, if player 1 plays hawk, what should player 2 play? Notice that if they also play hawk, both player 1 and player 2 will fall into the negative because b over 2 minus c is less than 0. And so both will come away worse off for it. However, if player 2 plays dove, even though player 1 will get all the resources, player 2 at least doesn't fall below 0. Hence, it's a better strategy for player 2 to play dove if player 1 has played hawk. Alternatively, if player 1 plays dove, then player 2 should always play hawk, because in this case, they would be getting the full benefit while player 1 gets no benefit, and if they play dove, they would only be getting half of the benefit. This is called a pure strategy Nash equilibrium. That is, where both of the strategies are maintained at exactly equal frequency. Because player 1 plays hawk, you always play dove. Player 1 plays dove, you always play hawk. So those two strategies can persist in the population at a pure equilibrium. The Nash part comes from the economist John Nash, who you might be familiar with. There was a famous movie called A Beautiful Mind made about his life. He's the economist that first came up with the idea of game theory. Okay, so those are two simple cases in which either hawks always win or you can get a perfect equilibrium between two pure strategies. But what about a mixed strategy? So for a mixed strategy, let sigma be the probability that player 1 plays hawk, such that 1 minus sigma is the probability that they play dove. So is there now a mixed equilibrium strategy, such that player 2's response to player 1 can depend on the probability of whether player 1 plays hawk or dove? So if player 2 plays a pure dove strategy, this is what we expect to happen. So since sigma is the probability player 1 plays hawk, then if player 2 is always playing dove, then this first term is 0, right? Because they gain nothing if they play dove. Plus 1 minus sigma, and the 1 minus sigma being player 1 plays dove, and since player 2 always plays dove, then the benefit here is b over 2. Now, if player 2 plays a pure hawk strategy, it's sigma multiplied by b over 2 minus c, because again, sigma is the probability player 1 plays hawk, and since if they both play hawk, then the benefit to each is b over 2 minus c, plus the probability they played dove multiplied by b. In this case, since player 2 is playing a pure hawk strategy, they will always win if player 1 plays dove. To see what the equilibrium is, we just set these two equal to each other and then do some simplification. What we find is this mixed equilibrium strategy occurs when b over 2 is equal to c over sigma. If we want to know what the frequency of the benefit and the cost needs to be for an equilibrium strategy to be reached, then all we need to do is solve for sigma. Sigma, again, being the probability that player 1 plays hawk. In this case, sigma is equal to b over 2c. That is, if the probability of player 1 playing hawk is equal to b over 2c, that is the benefit divided by twice the cost, then you have what's called a mixed strategy Nash equilibrium, where both of the strategies can persist given that that probability is equal to b over 2c. So now we've seen how to play the hawk-dove game. It's a very simple game, again, assumes that each one of the players behave in a rational fashion. We have seen that if b over 2 minus c is greater than 0, then hawks will always win. But if b over 2 minus c is less than 0, then there are at least two different stable strategies. One that is a pure stable strategy, assuming that player 1 always plays purely. And then second, there's a mixed strategy equilibrium that equilibrates around the probability of player 1 playing hawk as b over 2c.
Despite his success working with Maynard Smith, George's spiral into absolute abandon for his own life, turning everything over to God as he saw it, continued. His charity had left him with virtually no money. He wrote to Maynard Smith that fall that disaster is at hand, by which he meant the moment he was completely out of control and his fate would be decided by God. He wrote, quote, "The encouraging part is that I am now down to exactly 15p, and my visitor's permit for staying in the UK expires in less than a month. Thus, I reassure myself by telling myself that God's standards of disaster will shortly be satisfied. I look forward eagerly to when the 15p will be gone." Maynard Smith was concerned. He wrote back, quote, "I have less faith than you do that the Lord will provide. Please let me know at once if I can help." Bill Hamilton was also worried and wrote to George that if he got evicted, which was simply a matter of time at this point given he had no money or any intention in earning any, he could come and stay with him in Berkshire. He wrote to George, quote, "If there is an Almighty, I think you mistake his ways." But George was beyond help. He'd stopped eating, living off barely more than a pint of milk a day. He completely abandoned his thyroxine medication and refused to see a doctor. If he were to live or die, God would decide. Near Christmas of 72, a neighbor found George Price collapsed on the stairwell of the apartment building. He was rushed to the hospital and pumped full of thyroid hormones. The doctors report that he was in a state of starvation and malnutrition. He stayed in the hospital through Christmas, only to be released in January of 73. The thyroxine treatment must have recovered his mental state, at least for a time, because he started writing letters to his children again. He wrote to his daughter Anna Marie, quote, "I'm sorry I deserted you like that, and I'm sorry I was such a poor father to you. Looking at your picture now makes me wish I could do it all over again. You were a very sweet little girl, and I did wrong to leave you and then was very neglectful to you afterwards. I wish there was some way I could do a little towards making things up to you." To Bill Hamilton, he wrote, "I'd love to see you again, Bill. You are one of the people whose company I enjoy." He wrote to several old friends at the time, apologizing for being brash, for lashing out at them in the time just after his conversion, when his own righteousness was at its peak. He felt that now he understood, having had his closest brush with death, what Christianity was really about. He wrote to an old girlfriend about a vision he'd had in the West Tower in London. Quote, "I began to have a faint, vague impression of seeing Jesus walking before me bearing the cross. 2 or 3 times since, I have felt that he gave me the message, 'Follow me.'" The message was that only through love and humility could George walk the true path of Christ. And that, like Christ, this path would be laced with pain and suffering. He wrote to his ex-wife, Julia, asking her to marry him, apologizing for all the terrible things he'd said to her, and that now that he was a disciple of Christ like her, things would finally be right. He wrote, quote, One thing I can tell you with much assurance is that you would find me much kinder than before." Julia refused. He proposed to several other women during this time, old girlfriends, acquaintances. Despite his dedication to being a disciple of Christ, he was clearly also very lonely. By 1974, George Price had given away everything he had and was evicted from his flat. He wandered the streets of London, homeless and alone. He wrote to his brother during this time, quote, "I have no home, so use my business address as a mail address. Usually I wear brown Levi's, sneakers, and a colorful shirt. Many times each month I find myself reduced to 1 penny, a halfpenny, or 0. Most of my possessions have been given away, including my watch and coat, but I'll have to pick up a coat somewhere now with winter coming on. Everywhere I go, I keep running into down-and-out alcoholics, to whom I give when I have anything, and with whom I sit and drink from their bottle if they offer me a drink. Increasingly, I find myself on the opposite side from the police. Many of my friends have done time, and I've been in a house that was raided and had my things searched. I usually wear a cross of some aluminum appearing or pewter-like metal around my neck, except that people keep asking me for it, and I've given away 7 of them, and I don't have any now, and won't be able to buy another until payday. I generally try to say yes." George would find himself in the poorest part of London in an area referred to as the Levy Triangle, a swath of demolished buildings, vacant homes, trash, and decay. The homeless dregs flocked here, squatting in the abandoned buildings. He moved into what had meant to become a cinema, but the project had been abandoned. The second-floor apartments had the walls demolished, and it was here with 2 other squatters that George would live out the last days of his life. You could often find George during these days on a park bench, telling stories to struggling artists, labor politicos, the various eccentrics and addicts that wandered these parts of London. They were all obsessed with George. They loved his incredible stories. He told them about the Manhattan Project, about Bell Labs and Claude Shannon, and how he'd worked on cancer imaging in Minnesota. He'd met so many famous people, Nobel laureates and famous geneticists, physicists, senators. He'd been a writer for Life magazine and even had a contract to write a book for Doubleday. He had papers published in the most prestigious scientific magazines and had worked out a miraculous little equation for understanding animal behavior. One of these artists was named Sylvia. She described George at the time as being gangly and unshaven, with rotting teeth and often unclean, who spoke in a high, squeaky voice. She enjoyed his stories, but he soon became infatuated with her. She told George, "I like you, but marriage and romance are out of the question." Nevertheless, George had written to Bill Hamilton that he was once again changing his life course. He was giving up his work on evolution and genetics. He instead was going to marry the new love of his life, Sylvia, it turns out, though he told Bill in the letter that the feelings weren't yet mutual, and move back to America to work on questions in economics. George spent Christmas of 1974 alone in his squat. He had finally booked an appointment with a psychiatrist and even gotten a job as a night janitor. But on a cold, snowy day in January of 1975, George Price took a pair of scissors to his throat. He bled out on the kitchen floor and was discovered by another squatter the following day, who, upon finding the body, ran through the halls of the dilapidated building, screaming, "George is dead. George is dead." Bill Hamilton was called to identify the body at the coroner's office. He wrote in his memoirs that he went to the squat where George was staying to collect any papers that might still be there. Quote, "Although the house was awaiting demolition, the electricity was still on. It mightn't have been too freezing for George when he was there all alone over Christmas. As I tidied what was worth taking into a suitcase, his dried blood crackled on the linoleum under my shoes. A basically tidy man, he had chosen to die on the open floor, not on his bed. That is how his life became dreamlike to me, and also how his colorful thread in my science and my life ran out. Many years before, when George was still writing for Think magazine, he aptly described himself, writing, quote, "Many of the most imaginative and important inventions have been made by outsiders, not employed in the field concerned, who have followed their own schedules and worked according to their own plan." While it's tempting to see George Price in this light, a kind of outsider genius in a Goodwill Hunting sort of way, this would be an incomplete picture. George's life was marked by numerous failures as well. Forays into computer science, information theory, retinal anatomy, politics, all of which he was repudiated as an outsider who didn't know what he was talking about. And so we shouldn't come away from George's life with the notion that he was, as he saw himself, chosen by God. Instead, George was a man who wandered far and wide. He tried his hand at many things, and once, in a cramped flat in London, came upon the greatest theorem in evolutionary biology. Was it his outsider status that permitted this? Perhaps. Not having been schooled in model building in the traditional population genetic way, maybe he was allowed to approach the problem differently. And in doing so, he saw selection in a new light. This enabled him to solve some of the biggest questions of the time, the evolution of altruism and spite, questions that had haunted evolutionary biology since Darwin. Was George's conversion to Christianity genuine or the result of mental illness, possibly aided by drug use? It's impossible to know, and maybe it doesn't matter. To George, the conversion was very real, and the outcome was the same. George's eventual suicide, while tragic, was not wholly surprising. He'd been writing about suicide since his botched surgery in 1966. It's tempting to point to this singular event as the cause of his later mental and physical decline, but even as early as his undergraduate years, his friends had remarked that there was just something a little off about George Price. In the end, the life and work of George Robert Price was both profound and tragic. For 20 years after his death, the gravity of his work was not appreciated. But in the years since, the Price Theorem has emerged as the most important equation in all of evolutionary biology. While it's tempting to remember Price as a man haunted by depression and perhaps even his own genius, these should not cloud or detract from his incredible contribution to the study of evolution. Thank you so much for being here. This video was inspired by the historian of science and Orrin Harmon's book, The Price of Altruism. It also drew heavily on Sean Rice's book, Evolutionary Theory, Mathematical and Conceptual Foundations. Links for both of these books, as well as to Price's papers, can be found in the description below. If you like what I do here, hit like and subscribe, drop me a comment, and I'll catch you next time.